Yes, students, today we are discussing interhalogen compounds. What those interhalogen compounds means, how can we prepare them, what are their properties, and how can we describe the structures of those interhalogen compounds. For that, I'm grateful for this teacher Edna Richard. Because of her, I am getting this content and that I am presenting now. This interhalogen compound are the molecules which possess two or more different halogen atoms. Who are halogens about which I am talking now? That halogen may be fluorine, it can be chlorine, it can be bromine, it can be iodine, or even it can be astatine. But as per our syllabus, we are restricting ourselves up to iodine. It's compounds between the halogens. And what is said? And no atoms of elements from any other group means other than halogen, nobody is there. Only a halogen and compounds between them. Such compounds are called as interhalogen compounds. Mostly these compounds are binary. Binary means they have only two distinct elements. Means if I consider chlorine as one element, then other element will be fluorine. Numbers may differ. It can be ClF, it can be ClF3, but atoms who are composed or who are combined are chlorine and fluorine. Chlorine and fluorine. It can be bromine also. It can be bromine and fluorine, or it can be iodine and chlorine. Just wait, Chetan. So such compounds where two halogens are involved, number of their atoms may be different, but type of that halogen, elemental form of those halogens will be two. Such compounds where only and only halogens are going to combine with each other. No other element, no hydrogen, no nitrogen, no carbon here in these compounds. Such compounds are called as interhalogen compounds. And why I say two? Because mainly these compounds are binary in nature. Therefore, I said two halogens are combining. Few examples are quoted here. For example, chlorine monofluoride. Will anybody suggest me the formula for chlorine monofluoride?
CLF.
Yes, absolutely. It is ClF. Other is bromine trifluoride. I am not saying these only are there. Such many compounds are there. Yes. What may be the formula for bromine trifluoride?
BRF3.
Yes, BRF3. Other examples. Names are also very simple. Interesting topic it is. Iodine pentafluoride. Yes.
IF.
What? Brilliant. IF5. One more. Iodine heptafluoride. Yes, formula please.
IF7.
Brilliant. IF7.
IF7.
These are the few examples. Yes, IF7. Such many compounds are what possible. Few examples are quoted here. Means here what I did in this portion. What are interhalogen compounds? Just a few examples I put in front of you. Shall I move next?
Okay, sir.
Yes, sir.
These interhalogen compounds, yes, very good. These interhalogen compounds are of different types. See, first type XY. It means two halogens are there, two different halogens are there. One halogen, one atom, other halogen, other atom. X represents one halogen atom and Y represents other halogen atom. Second type XY3 means one halogen X, only one atom. Other halogen Y, three atoms are there. I want to know answer from you. Just guess. What do you think? If around X 3Y are there, 3Y type of halogens are there, then who will be the smaller? X will be the smaller halogen or Y will be the smaller halogen?
Y.
Yes, right. Y should be what? The small. Accordingly, see XY5. X is larger. So 5Y which are smaller can surround. XY7. X is so larger that 7Y halogen atoms can surround. If you note here only one surrounding halogen, here 3, here 5, here 7, all are odd numbers and increase is there by +2, by +2, by +2. These are the different types of what the halogen, and whatever you have concluded, See, it is highlighted. Who is bigger? X is bigger. And that X is which kind of atom? Less electronegative halogen. Means if I consider ClF5 as interhalogen compound, then who is X? Cl is X. Who is Y? Actually, this one. F is Y. Among Cl and F, who is less electronegative? Chlorine is less electronegative. So that less electronegative atom will be X, and certainly it will be larger compared to more electronegative halogen. And say additional thing, Y represents smaller atom or smaller halogen, or you can say it is a more electronegative halogen. So students, in this portion I told you what are the types of halogens, actually interhalogens. XY, XY3, XY5, XY7. Who is X? Larger. How is X? Less electronegative. Who is Y? Smaller halogen. How is that Y? More electronegative. Yes, students, is this portion clear?
Yes, sir.
Yes,
Yes.
sir.
Yes, sir.
Yes, good. See, all these types and their examples are given. Their physical nature, whether they are solid or liquid or gas, those are given. Many times, semi-solid kind of the arrangement they do remain with. See here, XY kind of the halogens, if you pay the attention, those XY kind of halogens are mainly gaseous in nature, but there are exceptions. ICl and IBr, interhalogens by means of iodine, they are solid in nature. Here see, all three states are there. XY3, when central atom is chlorine, it is gaseous. When central atom is bromine, it is a liquid. When central atom is iodine, it is solid. Means you will understand as we go down means towards iodine, and if that iodine remains a central atom, then chances are there that such compound will be solid or maybe to a more extent liquid. About the XY3 category, it will be what the solid. Here also pay attention. XY5, there chlorine is a central, it is gaseous in nature. Bromine is a central, it is liquid in nature. Iodine is a central, it's expected to be solid, but it is liquid. Therefore, I said previously, it can be the solid or it can be liquid, but it will not be the gaseous in nature. But about IF7, iodine is a central, it is a gaseous in nature. Interesting thing, pay attention. When I consider iodine as a central atom, here see iodine central atom, it is solid. When category is XY category. When iodine is a central and category is SY3, XY3, it is solid. When iodine is central, category is XY5, means number of peripheral atoms are increasing. Now see, that solid is converted to liquid or solid is changed to what liquid? It is liquid in nature. When the type is of XY7 means more number of the other atoms are surrounding the iodine. For example, IF7, iodine is a central atom. The type is gaseous. So from solid we come to liquid and then we come to gas. As number of peripheral atoms increases, the change or shift will be from solid to liquid to gas. About this chlorine central atom possessing, there is no question at all because all are the gaseous in nature here. This one, all are gaseous in nature. About bromine, if you have to pay the attention, you will find one difference is there. About that BRF, it is gaseous in nature, but others are what? Liquid in nature. So this BRF you can consider as a one kind of the exception, or BRCl can consider one kind of exception. But as we are coming from top to down, the shift may be there from gaseous to liquid to solid. As we move from left to right here, means peripheral atoms are increasing. Then shift may be there from solid to liquid to gas. Students, are you following what I'm saying?
Yes, sir.
Yes, sir.
Yes,
Yes, sir.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay.
Yes, sir.
Now all these compounds are of the type X dash YN, means here you can consider XYN. Here instead of XYN, it is X dash is said. And what is this N? This N, it can be 3, it can be 7 here, it can be 5 here. It is ClF means is a 1. That N is odd number. X is always lighter halogen. See, lighter halogen in terms of the weight means its atomic weight will be less. Fluorine is lighter than chlorine, which is lighter than bromine, which is lighter than iodine. So that X, that's the central halogen atom, is a lighter. Sorry. X dash actually. X dash, not X. It is X dash. X dash. Peripheral halogen atom is the lighter halogen atom. Means compared to iodine, chlorine is a lighter. Compared to iodine, fluorine is lighter. That's the meaning of that statement. Then explanation is given. Since the smaller halogen, that is what X dash, are bounded around the larger X as the ratio of the radius. Means radius ratio rule. Last year you might have studied. What you come to know, as radius ratio increases, number of peripheral ions surrounding, means coordination number will increase. That only it want to say. Yes, students, from this slide, what are we concluding? What are the different types of the interhalogen compounds and how can we describe their physical appearance, gaseous, liquid, means this variation, and solid. It's a rough, it's not a perfect. And then it is said that N is always odd and X dash is that halogen which is lighter in nature, and that can be explained by means of the radius ratio rule. These points we have covered in this portion. Students, is it clear?
Yes, sir.
Yes, their physical state we have discussed. Now this portion we are not going in detail, but you should know some ideas about their properties, and therefore it is tabulated here. Excellent information is given here. Here first point is regarding appearance at 298 K, means it is room temperature. Means at room temperature it is colorless gas, ClF. If you see BRF, it is pale brown gas, means their colors also are given. If you consider BrCl in pure state difficult to obtain, means it remains what the impure, or you can say some conversion between them, solid and the gas or solid and the liquid, that interconversion and the other contamination may possible. It's about the ICl, it is a solid, it's a red solid. IBr, it is a black solid. So here if I consider XY type of interhalogen compounds, at the beginning when lighter central atoms were there, more electronegative central atoms were there, the state is gas. When we come to the less electronegative or larger central halogen, or less electronegative, larger, and one more point, what can we say? Those are heavier, heavyweight. Then from gaseous, we can get what the solid appearance. Now come towards these interhalogens where three smaller halogens are surrounding the central larger one. You see here Cl is a central, Br is a central, I is a central. Number of peripheral atoms are same, 3. Those atoms also are same here. Those are fluorines. You see here it is a gaseous in nature. If you come to the heavyweight central atom, that's a bromine, it is yellow liquid in nature. If you go to the further higher, we are finding it is solid in nature. So whatever the logic that we applied here for the argument for the existence of their physical state, we are finding from chlorine to iodine, as we move, physical state will change from gaseous to liquid to solid, means they are going to become rigid. Come to here now, interesting, I2Cl6. See, such formula we have not discussed. Actually, XYN category, it is a dimerization of ICl3, and it is a solid in nature. Now come to the interhalogens, where the 5 interhalogens are surrounding the central interhalogen, the ClF5, BrF5, and IF5. Here case is little different. Similarity is there, but perfect solid structure we have not obtained. See, here central halogen is chlorine, which is relatively lighter. Central halogen is bromine, little heavier. Central halogen is iodine. So as we go from chlorine to iodine, what we expect? Rigidness. It is there. See, it is gaseous in nature, it is liquid, it is expected to be solid, but it is also what the liquid, because other pattern also is applying. As the peripheral atoms are increasing, the solidification or solid state, I'm not saying they will not solid, we are talking about their existence at room temperature. At room temperature it is liquid in nature. Now last, that's the interhalogen, where 7 small atoms are surrounding the central atom, that's the iodine, and it is, as per this logic, it is expected to be solid. As per this logic also, it can be liquid or the solid should be solid, it also should be liquid or the solid. But what is observation? It is gaseous in nature. So which factor is dominating here? Peripheral atoms are, if are more, then the rigidity will be the less. Liquid or the gaseous state will be there. It is about the physical appearance of these compounds. Is this point clear? Actually, it is indirectly repetition.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Yes. Now the second point, that's a stereochemistry. Means it's the arrangement, spatial arrangement, three-dimensional arrangement. Different shapes are given. I keep this point pending. It is included in syllabus. Structures of these interhalogens with respect to V.S. EPR theory. I want to cover it at last. Let me complete the remaining portion. Then I will come to this portion. As per their physical existence, you will find their melting point and boiling point. Those are in terms of Kelvin. This 117 Kelvin is a melting point, means room temperature, not only is that low temperature it melts, very low temperature it melts. Therefore, existence at room temperature is in the gaseous form. And see the boiling point, more than the melting point, certainly it will be there. If you have to compare their physical existence, then what you can say? See here, it is not a minus sign. Here, whatever you are getting, it is a nearly 293. Likewise, they said. See, just for comparison purpose, I take the boiling points. 173, 293, 278, 300. If I talk about this only, this 5, you will find here is some issue about the chlorine, fluorine, interhalogen, or chlorine monochloride, bromine monofluoride, and bromine monochloride. What are we finding? From fluorine, if you come to the chlorine, physical constant decrease. But if I talk about the central halogen as a chlorine only, peripheral halogen chlorine, then here 278, it increases to 373. From chlorine, if I go to the iodine, here also it is what the increase. So here only what you are finding, only the little change. Otherwise, generally what you are finding as we move from the chlorine to iodine as a central halogen, the boiling point increases. If boiling point increases, then chances are there it can exist in the liquid form or it can exist in the solid form. So at the basis of physical constant, further clarity about their physical existence will be there. Let us compare this now. One more example. Here 5 smaller halogens are surrounding the central halogen. If I move from chlorine to bromine to iodine, what I am finding? Boiling point increases. So whatever the thumb rule that we were with for the physical existence, that can be validated by this melting point and boiling point concept. If for that, more clarity will be there. Yes, students, are you following what I'm saying?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, good. Thank you. If repetition necessary, you can ask for that. It's a very important from thermodynamics point of view. Here they said, actually this what they wrote there, I'm writing there. Delta F H naught means what it may be. H means what?
Enthalpy.
Yes. And delta F H naught may be H naught, not for standard. Delta for what? F for what?
Enthalpy.
Yes, enthalpy change. And F for what? Just guess. What are forming there? Molecules are forming. Bonds are going to establish. Bonds are going to form. Then what can be the meaning of delta F H naught? F, what can be the Right. Formation. It is called as enthalpy of formation. Enthalpy change during formation of what? These molecules. Whatever these molecules we are discussing, no, their formation. If you note it clearly, students, can you read that clearly on your mobile? Whatever that figures are there, or shall I magnify? Can you read now?
Yes, sir. Yes.
Yes. You will note all these, whatever the values are there, all are negative. Exception is there. It's a BRCl. By the way, you are finding here, it is impure in nature. Means exactly stability is not there. Therefore, it is said was a impure nature. Otherwise, all where this enthalpy change, enthalpy for what formation is negative. What does it mean? Enthalpy change is negative. What is the meaning of that?
That is exothermic reaction.
Right. It is an exothermic reaction, means energy is liberated, energy is furnished out when during formation of molecule, when during establishment of bonds, formation of bonds. Now answer for my question. Because of loss of energy, because of liberation of energy, because of exhaust of energy, that molecule will be stable or unstable.
Stable.
Unstable.
It will be stable. It means negative sign indicates stability. It means more negative that delta H value is, more will be the stability. More negative delta H F naught you can consider different way of representing. What will be there? More will be the stability. Yes, students, are you following what I'm saying?
Yes, sir.
Yes, sir.
Yes, sir.
So if you compare these one atom surrounded interhalogens, CLF, VRF, CL, BRCL, ICL, and IBR. Out of that, don't consider BRCL, except this. As we move from left to right, here chlorine and fluorine are there. Here bromine and fluorine are there. Among these two, because fluorines only are there, I'm asking. Among these two, who is more stable? CLF is more stable or BRF is more stable?
BRF.
Yes, BRF is more stable. Similarly, see logic, we have to apply logic and we have to explain that. Here I am talking about ICL minus 23.8 kilojoule per mole and IBR minus 10.5 kilojoule per mole. Answer for my question. Who is more stable? If my question is not clear, you can ask me to repeat.
Sir, please repeat.
Okay. Listen carefully. It's a ICL, energy of formation minus 23.8 kilojoule per mole. It's a IBR, energy of formation minus 10.5. Means actually enthalpy of formation. Who is more stable, ICL or IBR?
ICL is more stable.
Right, ICL is what more stable because here more energy liberated compared to IBR. Similarly, I hope and expect you can work about the remaining interhalogen compounds regarding enthalpy change of formation. Next point here, because it's related, bond distances. If you see the bond distances, when more stability is there, more energy comes out, more negative enthalpy change is there, bond distance was expected to be what the increase. You will find here. So one of the conclusion, one of the factor. What is happening here? These two you can compare. ICL and IBR. Who is more stable? ICL is more stable. So bond distance is what? Less compared to IBR. Bond distance is less means they are closer. Here exception is there. Exception reasons are there. I'll discuss that. Bond distance here it is more. So it should be less stable. But what are we finding? It is more stable. Means bond distance is one of the factor. Other factor is the electronegativity difference. Because of more difference in electronegativity, stability also will increase. So bond distance is one of the factor. So don't get indulged with too much. But these values will help you to compare their formation constant or formation energy, enthalpy change or formation and these bond distances. Further example, let me consider these pentafluorides. What are we finding? The stability is going to increase. So what is expected? Bond distance should decrease. So here see basal and other basal and axial. These two bond distance, apical or axial, different distance. I'm talking about the only one at this moment. The basal bond distance in CLF5 is 172, BRF5 178, IF5 187. So what are you finding? Where is there less bond distance? Here is less bond distance. So it is expected that CLF5 should be more stable. Apply this logic and see here. Is CLF5 more stable? The conclusion is it is not. Therefore, I am saying bond distance and stability are related but more other factors are there. Those are related about the stability. Therefore, those things are not, because size of the atom also matters here. Extent of overlap also matters here. And therefore, being chlorine is smaller compared to bromine, compared to iodine, here bond distance is less. Here bond distance is little larger. Here bond distance is further larger. But bond strength is a measure of the attraction, total net attraction, and that depends upon extent of overlap, that depends upon electronegativity difference, that depends upon affinity between the two atoms which are combined to form that bond. But for your information, all things are given. Here you will find the basal and apical, terminal, because here, and bridge. Why bridge? Because it is the separate kind of the interhalogen they have considered, I2Cl6, which is formed from 2ICl3. So there, as like B2H6 remain the bridged kind. Otherwise, equatorial and the axial, such kinds of the nomenclature you will find. About the ClF5, it, in spite of apical, we can say it is axial also. There is no question. And in spite of basal, one can say equatorial. Molecular symmetry will allow us to consider those things. These are the various properties of these interhalogen compounds. Once again, you can go through this literature, all those values, compare them, and if question comes, we can have the discussion. Yes, students, is it clear now?
Yes, sir.
Yes, sir.
Yes, sir.
Good. Now see, properties of these interhalogen compounds. We can find these interhalogen compounds in vapor, solid, as well as fluid, means liquid state, you can say. Just I'm reading those properties. These compounds are unstable solids or fluids at room temperature. Few compounds are gases as well. Example they have given, ClF is a gas. On other hand, bromine trifluoride and iodine trifluoride is solid and liquid. This property in detail we have discussed in the above table. These compounds are covalent in nature. It is very important one. Covalent concept means there is overlap between, if I consider say a large iodine, it can get surrounded by means of small fluorine atoms, and those small fluorine atoms are represented by red orange color. It's a one, it is second, and it is third. What is here? It is overlap region, common region, and because of that overlap, we can say there is a covalent bond. Covalent bonding is there between those interhalogens. Next point. These interhalogen compounds are diamagnetic in nature. Answer for my question. When can one molecule be diamagnetic? What is the essential condition of diamagnetism? There should be or there should not be. Diamagnetic nature means what? In molecular orbital theory, we have discussed that last year also in detail. We have discussed this point. When can one molecule be diamagnetic? Or you can answer, when can one molecule be paramagnetic?
Repel magnetic property.
Yeah, that is true. They repel the magnetic field of induction, or they repel. But from chemistry point of view, from electronic or configuration point of view, what will you say? There should be or there should not be. In that way you can answer.
Paired electron.
Yes. If that compound or molecule should be
Unpaired
diamagnetic,
electrons.
all electrons should, yes, help me. All electron should be paired or unpaired.
Paired.
Yes, all electrons should be paired. If unpaired electron remains, any unpaired electron, if single unpaired electron remains, then it will be paramagnetic. Our conclusion is those are diamagnetic nature because all electrons are paired. Why are they paired? Because the bond pairs and lone pairs only remain in such molecules. Bond pair means here iodine and fluorine, two electrons are there, pairing is there, here pairing is there, here pairing is there. And in case if lone pairs are there, then lone pairs also is a pair. Unpaired electron, there is no scope to find or exist the unpaired electron. Therefore, they are not paramagnetic, or I can say those are diamagnetic in nature. So it's just a simple explanation why those are diamagnetic in nature. These compounds, interhalogen compounds, are very reactive. One exception to this is fluorine. This is because the AX bond in interhalogen is much weaker than X bond in halogens, except for FF bond. I give explanation to you. We are comparing the reactivity of these interhalogens with respect to halogens. For example, if I consider say ClF as one interhalogen compound, or ClF3 or ClF5 as interhalogen compound. Respective halogens, which one? Cl2 and F2, respective halogens. These interhalogen compounds are very reactive compared to whom? These halogens. What is exception? Fluorine. Means what I want to say, ClF3 is more reactive, but not as reactive as fluorine is. ClF3 is more reactive compared to whom? Chlorine. So fluorine is a exception. F2 is a exception. It itself is more reactive. Why? Because the bonds, that's the AX bond, which remain in interhalogen. If I consider ClF3 and ClF bond, this bond in interhalogen compound is much weaker. It is a weak bond. Answer for my question. If bond is weak, then it will be easy to break or difficult to break.
Easy to break.
Easy.
Yes, it is easy to break. Easy to break means whatever the reacting components are there, reacting species are there, atoms are there, they will come out and they will find other, they want to find other friend, means it is an indication of their reactivity. Bond will break, other reaction will form. Therefore, they are reactive. Why are interhalogen are reactive? Because bond dissociation energy for interhalogen compound is less compared to respective halogen. Exception is there, that is the fluorine. Yes, students, are you understanding what I am saying? If any question, feel free to ask. If you are not understood, say accordingly. I will repeat. Yes, students, waiting for your replies.
Sir, please repeat.
Okay. Pay attention. Interhalogen compound. Give me any example of interhalogen compound. Any example of interhalogen compound?
BRCl.
Yes, BRCl. This interhalogen compound is obtained from which two gases? One is
Bromine.
Br2, yes, bromine gas, and other is
Chlorine.
Cl2 gas, Cl2. Yes. What is found? This BRCl is less stable, or more aggressive, more reactive. Less stable, therefore they are reactive. More reactive. Compared to whom? Compared to parent halogen, bromine. Compared to whom? Parent halogen, that's a chlorine. It is a meaning of that statement. Why it is so? Because the AX bond, means this BRCl bond, is much weaker, is weak compared to XX bond, means this BR-BR bond or Cl-Cl bond. Compared to this BR-BR Cl-Cl bond, this BRCl bond is weak. Bond is weak means easy to break. Easy to break means components or constituents will react with other thing. So therefore they are reactive. So point of interest is interhalogens are very reactive compared to halogens. But for that exception is there. And that exception is which gas? Help me. Who is exception?
Fluorine. Fluorine.
Fluorine.
Fluorine is exception. Is that statement clear now?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Very good. Now see the next point. The structures of these can be explained by V.S. EPR theory, and I want to cover it next time. About structures, last lecture I will invest for that. Let us know their preparation. Two main methods are there. First, direct mixing of halogens, and other reaction of halogens with lower interhalogens. Means F2 and Cl2 are combining and forming their respective interhalogens is a one method. Other method, ClF as a one of the interhalogen compound will combine with F2 to form ClF3. That is the second method. The halogen atoms react to form interhalogen compound. Example is given here. When a volume of Cl2 reacts with an equal volume of fluorine at 473 K, the resultant product is chlorine monofluoride. Means when a chlorine reacts with fluorine in how much proportion? 1:1 proportion, equal quantity at 473 Kelvin, you will get chlorine monofluoride. In other cases, halogen atom reacts with another lower interhalogen to form an interhalogen compound. For example, fluorine reacts with iodine pentafluoride at 573 K to give rise iodine heptafluoride. Means if I have to write that reaction, then what I can say, F2 reacts with this iodine pentafluoride, I F5 at 543 K to produce IF7. Further few reactions are here. You can take snapshot also and you can work on these reactions. Means two methods are there. One method, direct combination. Here see, direct combination, direct combination, direct combination, direct combination of halogens. It is a one method. Second method, halogen combines with lower interhalogen to produce larger interhalogen, higher interhalogen. Yes, students, is it clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now separately, iodine monochloride, how can it be prepared? I2 plus Cl2 gives ICl. And structure, see, here large iodine is there, large iodine, and here small chlorine is there, and interaction region is there, covalent bond is there, linear structure is there. Detailed information about it also given. It is a red brown chemical. Because of difference in electronegativity of iodine and chlorine, ICl is highly polar. Highly polar means what? I plus and Cl minus. Charges are there, see. I plus and Cl minus. Iodine carries positive charge and chlorine carries negative charge. Why iodine carries positive charge? Because it is electropositive compared to chlorine. Likewise, students, you will understand the preparation of BRF3 structure we are discussing in detail. Don't worry about that. Here, straw colored liquid with pungent odor. It is a very important property from industrial application point of view. It is a powerful fluorinating agent. Means it can give the more fluorine, and it is used to produce industrial application. Uranium hexafluoride UF6 in nuclear chemistry. If you have studied enrichment of fuel, naturally the uranium 235, which is necessary for the fission, remains to less extent, only to the 0.7%. We want to enrich to 2.5%, means almost 3 times or 4 times. And for that purpose, we need to convert that uranium to gaseous form. And while forming that gaseous UF6, we need source of fluorine. And that source of fluorine is a BRF3. Important application while preparing or processing on the nuclear fuel. Next compound, BRF5. Interesting structure is represented. We're discussing this all. How can we produce a diet combination, reaction conditions, all are given. You can go through them later. Yes, students, is it possible that you will study it later?
Yes,
If you have described here, then you can bring it to my notice. I'll describe. Okay, you work, any problem comes, that we will discuss. And see here, important. It is extremely effective fluid compared to BRF3, BRF5 is effective. Converting most of the uranium compounds to hexafluoride at room temperature, like BRF3. Actually, more than that, because large number of fluorines are there. See, next one, iodine heptafluoride, and its a synthesis or its preparation is based on second method. What is second method? Lower interhalogen compound will combine with halogen to produce higher interhalogen compound. IF5 is a lower interhalogen producing IF7. It's a strong oxidizing agent. Oxidizing agent itself undergoes reduction. Why? Because in IF7, iodine is at its extreme high positive oxidation state, I plus 7. I plus 7 chances are there can convert to I plus 5, or can get converted to I plus 3, or can get converted to I plus, or can get converted to I minus. Everywhere you will find it should accept electrons. It will accept electrons, it will undergo reduction. I plus 7 will undergo reduction. IF7 will undergo reduction. Means it is oxidizing agent. Oxidizing agent itself undergoes reduction and is used because a high oxidation state of iodine is there. It is used to prepare the periodic acid. Such interesting applications also are discussed for the few compounds. Okay. Now shapes of all interhalogen compounds that I want to discuss next time. Firstly, let me go through the uses of these interhalogen compounds. It is not as a part of a syllabus thoroughly, but shortly we will go. It is important one. These interhalogen compounds are non-watery solvents, means non-aqueous solvents. As like water solvent we can use, no. Likewise, IF7 or ClF3 we can use as a solvent. These work as a catalyst for many reactions. Here, industrial application, UF6 can be produced. Here, while giving example, I had given BRF3. Here, ClF3 is example given. ClF3 to produce UF6. Means you can consider ClF3, or you can consider BRF3, or you can consider BRF5, all are the sources of fluorine to undergo the fluorination of uranium to produce UF6. That's our point of interest. These compounds are the fluorinating compounds, fluorinating agent. These are the applications of these compounds. So which are the applications? Non-aqueous solvents work as catalyst for fluorination of uranium especially, as a general fluorination is said. So students, today I had covered which points? First point, definition. Second point, types. Third point, right from physical state, the properties, all properties of the interhalogen compounds that we discuss. Fourth point, preparation. Two methods are there, one direct and other indirect. Indirect means from lower interhalogen we can form the higher interhalogen. Fifth point, structure I am going to discuss next time. Uses. These are the points we have covered today. Can you prepare notes, students? Waiting for replies. Muskan said yes, Ganesh said yes, Pratiksha said yes, Alia said yes, Neha said yes, Amisha said yes, Ankita said yes, Shubhangi said yes, Chetan said yes. Yes, means all students are saying yes. Very good. I give some time to you for the preparation of the notes. Today maybe the assignment I will display. Recording you will find by night. So shall we stop now?
Yes, sir.
Okay, in chat box all are saying yes. Okay, good students. Now I declare here today's session is over. I stop the recording. Quit now.